All right, and we're back. Let's talk alkenes and alkynes. Cool. So, topic of this video is alkenes and alkynes. So, going back to the previous video on alkanes for just a minute. Remember alkanes, and here I'm just going to make a little propane for us. Alkanes contain carbon to carbon single bonds only. So here's our buddy propane. Cool. Alkenes and alkynes, instead of ending the names in ane, they'll end in ene or in ine. So here's the facts about alkenes. They contain a carbon-to-carbon double bond. I should say less, I should say fewer. They have two fewer hydrogens. We'll look at how we can make a formula out of that. It's actually a formula that's in your data sheet, which is nice. So they contain a double bond. They have two fewer hydrogens. They're still made out of carbon and hydrogen. The ending part of the word, in other words, the suffix, instead of ane, the suffix is ene. And the last thing, we gotta have the double bond in the main chain. We also have to include the address of the double bond. Remember, in other words, remember how we used numbers to say the address of branches on alkanes that have branches? Same deal here, only in this case, we also need to understand and explain where the double bond lives. So I'm going to draw an alkene. Not going to use a red marker, that's for sure. Okay, let's just do an alkene that has, let's see, let's do 4 carbons. And I'm going to go ahead and put the double bond here. Now, since this is a nice small molecule, it's not really big, what I'm going to do is I'll draw all the hydrogens on here. I'm going to do tickies from now on, but I have a point. I have a point to make, and I'm going to say it. So we got all of our hydrogens almost done. I'm not going to draw one here. This is the first part of the point I'm going to make. Remember that a carbon only has 4 bonding capacity. In other words, you only get to draw 4 lines coming out of a carbon. So I already have 4. I have 1, 2, to the hydrogen is 3, and to the carbon on the left is 4. So that's done. Now we look at our carbon on the end, this terminal carbon. It's got 2 lines coming out of it already, and therefore it only has bonding capacity for 2 more lines. Done. Now let's get on to naming this bad boy. It's going to be a little bit more difficult than an alkane because of these 2 facts that we need to include. So the first thing I'm going to do is I look at how many carbons this thing is. And there's no branches here, so we won't worry about that for now. So we have 1, 2, 3, 4. So I know, and if I don't know, I go into my data book and I check it out, and I see that when something has 4 carbons, it is called bute. I see there's a double bond here, which means that it will end in ene. If you're wondering why I haven't put anything here, why I put a space, it will become apparent, I guess, right now. So let's switch to a different color. Let's switch to like an orange, I guess. Yeah, let's do orange. So yes, my double bond is here. But I have to say the address of the double bond. So I can either count 1, 2, 3, and as soon as I hit a carbon that has the double bond on it, that's the number I use. So if I'm counting from left to right, 1, 2, 3, then I hit my double bond, and I might be tempted to call this bute 3-ene. But it for sure is not bute 3-ene. Remember, our goal is to get the smallest numbers possible. So here, I would rather count 1, 2, 3, 4 this way. And so that means my double bond is on carbon 1. That gives us the molecule called bute 1-ene. And you might be wondering, okay, Lorenz, like, what does a bute 2-ene look like? I'm sure you're just dying to know. So I'm going to move the double bond over by 1, and I'm going to make tickies for the hydrogens. Here, if I look at this carbon, it's already got 3 lines coming out of it, so boop, it gets a hydrogen out there, and boop, that one gets a hydrogen out there. So in order to name this molecule, again, it's still 4 carbons, so it's still bute. It's got a double bond, so it is still ene. And then all we have to do is check out, okay, where the double bond is at. And the double bond in this case, and it doesn't matter which way we count. If I count 1, 2, 3, 4, the first carbon that I step onto that's got a double bond is carbon 2. And if I go from the other way, 1, 2, 3, 4, same deal. It's still carbon 2 that has the double bond on it. So that molecule is called bute 2-ene. You might be thinking, who cares? Like, what is, honestly, like, what is the difference between this molecule and this molecule? It's like, all we did is we moved a double bond over from one carbon to the next. Here's the deal. These guys, these 2 molecules, are going to be a little bit different in their reactivity and in their boiling and melting points. So, yes, they are their own molecules. They're unique. They're different. They're not the same. However, they are similar in a very important way. If I take a look at this and I count all my C's and all my H's up, I have 4 carbons, so this will be the molecular formula, or rather the empirical formula C4. 1, 2, 3, 4, 5, 6, 7, 8. 8 hydrogens. We look here, still got 4 carbons. Nothing's changed. 1, 2, 3, 4, 5, 6, 7, 8. Oh, hey, what? Look at that. These have the same numbers of carbons and hydrogens. And when we have that, it's a special word that we use. Call them isomers. And this doesn't just apply to carbon and hydrogen. In our case, considering that's all we are dealing with, the molecules we're looking at only have carbon and hydrogen. But if you have the same number of each type of atom, but everything is connected in a different way, those are called isomers. And the longer your chain, the more kinds of isomers you can get. So yes, they are different molecules, but they are made out of the same number and type of atoms. So you might notice that when there's 4 carbons, there's 8 hydrogens. I'm going to do another example for you of an alkene. So same type of molecule that we just saw. Let's do, I don't know, let's do a pent. So 1, 2, 3, 4, 5. And then tick, 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 tick. So we'll name this guy, and then we'll look at the formula. So it's 5 carbons long. I look in my data booklet, or I have it memorized in my brain, that a 5 carbon thing is a pent. And since it contains a double bond, it's an ene. And then we say, okay, where's the double bond at though? If we count from left to right, 1, 2, 3, it would be on carbon 3. So if I count this way, it would be called pent 3-ene. But remember, we're always in the market to try to get the numbers as low as possible. So if I do this, I will count the opposite direction, 1, 2. So that means that this molecule is pent 2-ene. Let's do a quick add up of all of the C's and H's in here. So 1, 2, 3, 4, 5, 6, 7, 8, 9. We got 10 H's and 5 carbons. So C, 5, H, 10. So for an alkene, the formula follows a pattern. If my number of carbons we call N, the number of hydrogens we have is always twice that much. So if I had something like, I don't know, an alkene that had 15 carbons, if I want to know how many hydrogens it has, I multiply by 2, which means it would be C15H30. So this follows a pattern, and you may be given something like a formula like this, and the question may be asked to you, hey, is this an alkene? Is it an alkyne? Is it an alkane? What's going on with that? And so you'd use your formulas in your book to determine, is the number of carbons and hydrogens, does it match what we would expect from an alkane, an alkene, or an alkyne? So let me continue on. I'm actually going to get a new page going. Let's do a branched alkene. So it's going to be an ene, but I'm going to throw some branches on it as well. And I'm going to get weird with it too. Let's see, what else? What other fun can we put on this bad boy? Let's see. Sure, let's throw a carbon up there. Let's throw a carbon down there. Oh my goodness, what an absolute mess of a molecule. It's not that bad. I shouldn't complain. Make my little tickies for hydrogens. Bop, 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 bop. Bop, bop, bop. All my little tick marks. That one doesn't get any hydrogens at all because it already has 4 lines coming out of it. Oh my goodness, this is a big boy, but that's fine. So first thing we must do in order to name this molecule, and we'll color code it like we've been doing before, we got to find the main chain. So this is one where I've on purpose made it so you can't just go left to right, because that's, yeah, we need to exercise our brains a little bit better. So if you went left to right like that, you're so wrong. It's awful. It's embarrassingly wrong. So problem with this, first of all, it's not the longest chain. Second of all, it doesn't even, we didn't walk down the double bond. We have to do that. So I have to include my double bond. So let's see what's the longest line of carbons we can get that includes the double bond. Let's see, 1, 2, 3, 4, 5, 6. Okay, 1, 2, 3, 4, 5, 6. It looks like 1, 2, 3, 4, 5, 6. It looks like 6 is the best that I'm going to be able to do. So there we go. There's our main chain. So it is 6 carbons, which means that it is going to get the name hex. I'm going to put a space for the number that tells me where the double bond is. And since it contains a double bond, it is an ene. So we know it's a hex something ene. Let me switch to orange and we'll figure out where the double bond is. If I go left to right on my main chain, 1, 2, 3, it's on carbon 3. If I go the opposite direction, 1, 2, 3, it's on carbon 3. So that means that regardless of the way that I count, it's carbon 3. I always pick my counting to get this the lowest. It's more important than the branches. It has what we call priority. Now, I'm not going to spend any time on it because it's not necessary in Science 30, but there's a whole zoo of different types of molecule features. We call them functional groups. You'll see them later. We'll get our nose into a couple of them. Unfortunately, not literally, because one of the labs that we do is to make cool smells, and unfortunately we're not going to be able to do that this year. There's no real way to do a lab where we prepare smells. I would definitely not let you do that experiment at home, even if you had the materials, which you don't. Anyways, so on to the rest of this molecule. So we wanna, once we've, since this is in the middle, and it doesn't matter which way we count. The next thing we care about is to make sure that the branch numbers are the lowest. So let's just take a look at the branch numbers. So we have 3 branches on here. 2 of my branches are methyl groups, and 1 of them is an ethyl group. Now when you do these, they take a lot less time, but when you walk through them, it does take some time to explain what's going on. So the numbering rules that we learned in alkane, they also apply to the branching for alkenes. It's the same thing, literally the same idea. So let's see, if I count left to right, I have, okay, carbon 1, carbon 2, there's something on there, carbon 3, there's something on there. So 2, 3, 4, 5. So this would be a 2, 3, and a 5. Let's see what happens if I go the other way. 1, 2, 3, 4, 5. If I count this way, it would be 2, 4, 5 instead of 2, 3, 5. So which one is better? The one with the lowest numbers. So 2, 3, 5. So I'm going to count my carbons. 1, 2, 3, 4, 5, and 6. And now we have to name these. So in alphabetical order. So here is an ethyl group. It starts with E. Where does it live? on carbon 3. So this guy is a 3-ethyl. And now the methyls, I gotta kind of work on them together. So there's one on carbon number 2. There's another one on carbon number 5. So that means that I'm going to write 2, comma, 5. That tells me where they live. Then I'm going to write di. That tells me how many. And then methyl. So then we just have to place these into our name. And we do it in alphabetical order. So this will be 3-ethyl dash 2, comma 5 dimethyl. And I'm just going to kind of drag this over, make it a little bit bigger so it kind of fits the theme. Looks kind of like almost the same writing now. So this molecule, these names start to get very long. So it's 3-ethyl from here, 2,5-dimethyl, hex 3-ene. I'm going to do one more example of this, and then I'm going to let you go with the reassurance that alkynes are very similar. The naming is the same. So we'll go over the features of alkynes, and I'm not going to do naming for them because it's literally the same naming as an alkene. It works the same. Alright, so let's draw another one. Can't really get much, it can get crazier than that. But oh, I'm a monster. I shouldn't be doing this. Oops. And then, let's see. What do we want to do? Sure. Let's do that. So let's take a look at our longest chain first, because that gives us the guts of the name. If I go left to right, what do we have? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. That's still 7. 1, 2, 3, 4, 5, 6, 7. It looks like 7 is the best that I'm going to be able to get. I can't see any way of having an 8 that contains the double bond. So I guess we can just go for this one. Yeah, I thought I was going to go straight across. Nope. Went down. It doesn't change the name, it's okay. So since this is a 7 carbon, it's going to be a hept. Since it's a double bond, it is an ene. Then we find out which way gives me the lowest number, and then I'm locked into counting that way. You can't count one way for your double bond and then be like, oh, I'm going to count the other way for the numbers. Nah, dog, as soon as you commit to a specific number and a specific counting direction, you're locked in. So you can't change it. So we got a double bond here, so 1, 2, 3, or 1, 2, 3, 4. So it's 3. So 1, 2, 3, 4, 5, 6, 7. So this is a hept 3-ene. Okay, cool. Now the way that this turns out is actually kind of nice. We have 3 of the same kind of branch. They're all ethyls. There's 3 of them, which means that I use tri-ethyl So it's triethyl hept 3-ene. Now all we have to do is explain where do the ethyls live. One of them lives on carbon 3. One of them lives on carbon 4. And one of them lives on carbon 5. 3, 4, 5, triethyl hept 3-ene. Just to be completely nuts, I'm going to make the tickies on the carbon, or for the hydrogens, just to prove that it still has twice as many hydrogens as it does carbons. Am I crazy? Yes, the isolation has made me mad. Let's count these. So how many total carbons does this guy have? A lot. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. It's got 13 carbons. That means that I should be able to count out 26 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. Beautiful, 26. So the formula C13H26, it still obeys the CnH2n rule. So a big mess of a molecule, but it still works the same way. This is what's actually really nice about chemistry. I mean, it's nice about a lot of these sciences. There are rules, and they make your life easier. They're not just rules that you follow because, you know, I tell you to or whatever. They're rules that make communicating science ideas much easier. So same with acids and bases. Like, we use the pH scale all over the planet because it means something. It gives a way for somebody who runs a factory in Taiwan to make a specific chemical that has a certain acidity that maybe a buyer in a different country wants. Or maybe a researcher in one country, in Germany, is cooperating with a researcher in Nigeria. And they're doing a scientific paper. They need to be able to communicate what they're talking about. And so this is why we do this. It's because now we can communicate in this shared language of, you know, what molecule are you trying to tell me about? You write this for anybody who's in like university sciences anywhere around the world, they're on this. They will know what you're talking about. It's really cool. Alright, so just a little quick aside for alkynes. And I'm not, like I said, I'm not going to do the naming for them because they are the same as alkenes. The only difference is instead of your word ending in -ene, it ends in -yne, ein. So first big fact, obviously they contain a carbon-to-carbon triple bond, and they're, they end in -yne, and their formula, if we have a formula like this, the formula for alkynes is CN, and then it's H, and this is where we got to do a little bit of math, 2N minus 2. Alright, you've convinced me. I'm going to do a really simple alkyne. There we go. We get a hydrogen here, and we get 3 hydrogens on the other carbon. If you look at that poor carbon in the middle, it's all tied up. It's got 4 lines coming out. It's not bonding to any hydrogens. So this guy has 3 carbons. So it has a formula of C3, and then how many hydrogens? 1, 2, 3, 4, 4. Awkward, right? Like it's not even numbers. Does this work? Well, if C is 3, 2 times 3 is 6. 6 minus 2 is 4. So this obeys the rules. What will we call this guy? Well, that's a simple one. Meth eth prop. This is a prop because it's got 3 carbons. And it has a triple bond, which means it ends in -ine. If you're wondering, hey Lorenz, why didn't you put a number there? Well, think about it this way. If the triple bond was here instead of there, it would be the exact same molecule. Like these hydrogens would be over here, and they would no longer be over here. So it would just, in essence, it would be literally the same molecule, just rotated around. So I hope that clarifies some things about alkenes and alkynes. We'll be continuing all of this next week. So have a good week. Remember that you need to complete this homework on the weekend for Monday.